Okay, well, here we go again. This is kind of an ordinary problem about pushing a crate up a ramp. But what we want to do is find the final velocity that results from applying a constant horizontal force to this crate that is being constrained to move up a ramp that has, or an incline that has an angle alpha with the horizontal. So the numbers are given for the various parameters here. The mass is 10 kilograms for the crate. Coefficient of kinetic friction between the crate and ramp is a constant value 0.07, and the force is 100 newtons. Then the question is, what is the velocity of the crate after it has moved a distance of 10 meters along the incline? So we're going to move along the incline, and the angle alpha is 15 degrees. Okay, well, a key to the problem is decoding the forces and the angles through which they act, and then decomposing them into their components. So just understanding the trigonometry, it becomes important that if the angle alpha is between the horizontal and the incline, that's shown here, then it's also the same angle acting between the normal to the incline and the vertical. So the angle alpha is from the horizontal this way, but also from the vertical this way. So shown here are the various forces that are exerted on the crate by shrinking the crate to a point source, a point object, and then showing the forces that are acting on that point if we remove it from the environment. So when we take away the ramp, we have this normal force that is revealed, that is constraining the crates to move along the ramp. And then also there, of course, the force F persists there, that's being imposed, and then the weight mg. These are the forces that are acting on the crate. There's one other force that acts on the crate once it comes into motion, and that is the frictional force. And the frictional force opposes the motion, so it acts in the negative incline direction, and that opposing force, that frictional force, is magnitude is mu times the normal force. Sort of combining several steps here to determine this frictional force. If we sum forces in the direction normal to the incline, we can see that the normal force is the sum of the component of the applied force, normal to the plane, and the weight of the crate, normal to the plane. So N is equal to F sine alpha plus mg cosine alpha. And over here, that's what's shown as the net frictional force, mu times normal, which is mu times F sine alpha plus mg cosine alpha. Okay, so we've got a lot of things done there all at once. We've also decomposed this applied force into its two components, the one along the plane, which is F cosine alpha, and then the one normal to the plane, which is F sine alpha, the result we've already used in determining the frictional force. Likewise, the weight of the crate, mg, has two components, one normal to the plane, which is mg cosine theta, and then the one that is downward down the plane, which is mg sine theta. Okay, so each one of the forces that opposes the direction of travel will give rise to a negative force. So that will be both the weight component that's acting down the plane and also the friction that's acting down the plane will give rise to a negative work component. The applied force, external force, will give rise to a positive work term. So we'll use the work energy principle. The forces normal to the direction of travel do not have any effect, don't do any work. And so considering the external force, F cosine theta, F cosine alpha times the length traveled, L, is the work. If we consider the two forces that are normal to the incline, we talked about this before. The normal force has two components, one that's due to the applied force, one that's due to the weight. And so both of those contribute to the normal force, and that in turn contributes to the frictional force, because the frictional force is mu normal, so it's mu times F sine theta plus mg cosine theta times the length L. And again, this is negative since it opposes the direction of travel. And then finally, we have to consider the work done by the weight. The weight opposes, the component of the weight down the plane opposes the motion, and so there's a negative work contribution, mg sine alpha times the length. So those are the components of the work that are involved. We're going to equate that net work to the change in kinetic energy. Initially the kinetic crate is at rest, so the final kinetic energy, 1/2 mv squared, is the term that we'll need. So when we set these equal, W net is equal to change in kinetic energy, we can find an expression involving the velocity squared. So we can solve this expression for velocity squared. May actually be easier to evaluate this just to calculate term by term, since we have expressions for all of the work terms here. But you can put it all together, struggle through some algebra, and come up with an expression similar to 1.8 here. And then by substituting in the given numbers, you can find the final velocity of the crate after 10 meters of application of the force to be 11.2 meters per second.